Hi everybody! Today we're going to check out the Platonic solids, or the three-dimensional shapes that the Greek philosopher Plato theorized about. Now, before we can talk about three-dimensional shapes, we probably have to start in 2 dimensions. Every geometry student in high school will study the idea of polygons that are regular. And of course, if you have ever taught geometry, the key part of regularity is that a polygon, well, number one, has to be a polygon, right? It has to be closed, but it also has to be equiangular and equilateral. Right? There are those little equal angles, and these sides are the same length, right? Which creates this nice symmetry that helps us reason about these shapes sort of abstractly. For example, once we know that a triangle is regular, well, if we know that a triangle has 180 degrees inside, then if all of these angles are the same, they must be 60 apiece. Right, fairly simple stuff there. Right, same thing with the quadrilateral. We can realize that a quadrilateral is just 2 triangles being combined together, which means that its internal angle sum must be 360, which means that all of these angles right here must be right angles, right? They have to add up to 360 degrees, which means they're 90 apiece. Right, the pentagon, let me see if I can draw this well. There we go. Yeah, that's not bad. Let me see if I can get those lines a little straighter. Ooh, that's a lot nicer. There we go. The pentagon is 3 triangles, right, which means it adds up to 540 degrees, right, or 180 times 3. Right, and when we know that all of these 5 angles right here have to add up to 540, which means that each one is about 108 degrees. Alright, so cool. We have some lovely symmetry here. Everything looks really nice. We can reason about it abstractly, but we're really only in the 2-dimensional plane here. And what Plato thought about was how to take these things into 3 dimensions and still preserve this equiangularity and this equilinearity, right? This symmetry that makes these shapes so beautiful and nice to reason about. Let me put in those lines as well. Good practice. There we go. So let's take this concept of regularity and put it into 3 dimensions, right? Let's take regular polygons, right, these regular 2-dimensional shapes, and let's try to construct some sort of closed 3-dimensional figures with them where all of the sides of those closed 3-dimensional figures are regular polygons. So for example, here we have the tetrahedron, right? If we actually like sort of sketch in the lines we can't see, little dotted line here, we can see that the tetrahedron is a 4-sided figure composed of sides that are all equiangular, equilateral, or regular triangles. Same thing with this hexahedron, which is just a fancy way of saying a cube. Let's see if I can draw that a little better. The shift tool is really nice because it sort of enables you to like draw these really lovely straight lines. Been using it a lot in my online teaching. There we go. The hexahedron is just the cube. Right, but we call it a hexahedron because it has 6 faces, all of which are regular quadrilaterals, right, or squares. The octahedron is an 8-sided figure, right, so there we have octa, right, 8 sides, and those are also like regular triangles, right, so we could see the angle right here would be 60, the angle right here would be 60, the angle right here would be 60, and so on and so forth, right? We can see that the dodecahedron, right, or a 12-sided figure, is made up of a bunch of regular pentagons, right? So we know that this angle right here, for example, is 108, right? And we make up these little vertices right here. And then lastly, the icosahedron, right, my personal favorite because it is the only Platonic solid that has a vertice composed of 5 faces meeting together, which is kind of cool. The icosahedron is also made up of triangles. So let's formalize some requirements for what it means to be a Platonic solid, right? Or a solid made of regular polygons. Well, first things first, it has to be closed, right? It needs to actually be a solid, right? Something you could hold and not like crawl into the inside of that shape with any opening. So for example, let's take these triangles for a moment and let's see if my art skills will not fail me. Let's draw a little triangle side right here. Right, just sort of like a 2-dimensional triangle. And let's draw another triangle right near it, right? Imagine that this is like standing up straight. Sorry, I turned on sticky keys. Hang on a second. So let me draw some shadowing in here to really drive this home. So imagine that this shape right here is like sitting on the ground and this one is standing up, sort of forming almost like an L shape if you were looking at it from the side. Okay, well this is not a closed solid, right? Because you can sort of look at it from both sides, right? Even if we drew like another side right here and had it open, the idea is that you don't want to be able to get into the shape, right? It needs to be protected from all sides. The second requirement to be a Platonic solid is this idea that all the faces are the same regular polygon, which I already sort of discussed, so I'm going to gloss over that a little bit for the sake of time. The last sort of requirement we have here is based on these ideas of vertices right here, right? The little pointy parts of these shapes, right? And we need 3 faces to meet at a vertex at least, right? 2 faces won't give us that closed requirement that we want. Now, at those vertexes, or vertices, something special has to happen. And we're going to talk about this a little more at the next page. But basically, when we have a vertex, right, when we're looking at this stuff right here, the angles that meet up at that vertex have to be less than 360 degrees. Well, why? Let's take the example of if we make 4 sides that are cubes, or pardon me, that are squares meet at a vertex. Well, if I have a cube coming, or if I have a square meeting here, 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 and here, all of a sudden those 4 quadrilateral faces are now lying flat, right? They have no sort of curve to them, which won't allow them to meet any other faces anywhere in this Platonic solid, right? So that's a key component of what makes a solid a Platonic solid. Let's explore this idea of vertices summing to less than 360 degrees here. This right here is a flattened tetrahedron, right? And we'll notice that at any sort of point where things would sort of get folded up, we are at less than 360 degrees, right? We have 60, 60, and 60, totaling 180. Same thing with the cube, right? If we're folding up these quadrilaterals into the cube that should form, right, we still are at only 90, 90, and 90 degrees there, totaling 270 degrees, right? Oops, not a percent. Hang on a second. There we go. When we fold up this cube, right, we're going to be able to close the shape eventually. Same thing here. This is the flattened form, right, the 2-dimensional flattening of the octahedron, right, that 8-sided figure that's made up of regular triangles. And again, here we have 60, 60, 60, and 60, totaling 240 degrees of angles meeting at that vertex. Then we have our dodecahedron being flattened. And if you recall from before, the angle inside a regular pentagon is 108 degrees. If we have 108 degrees times 3 shapes meeting at a vertex, we have, I believe, 324 total degrees coming to a point there. And lastly, we have that icosahedron, right? 1, 2, 3, 4, 5 regular triangles meeting at a vertex. If we have 60 degrees per regular angle times 5, that gives us a total of 300 degrees. Now you might be thinking, well, if we have infinitely many regular polygons, shouldn't we also have infinitely many Platonic solids? And the answer is no, for the reason that, what if we try to put another triangle here and fold something up? Well, all of a sudden, we're at 360 degrees, right? Which means that those faces would all have to lie flat to come to a point properly, right? And any others would sort of make it concave, right? We would sort of fold the shape back down, not back up, so that it could connect with the other faces. We also might think, couldn't we use larger polygons? And again, the answer is no, for the fact that, well, let's say instead of using a pentagon, we started using little hexagons, right? Here's one little hexagon, very poorly drawn one, right? And let's say that we tried to connect it to another hexagon. 1, 2, 3, 4, 5. This is not great, but you know, it is what it is. we're going to try and fit another hexagon right in there, but we can't, right? Because here we have a regular hexagonal angle, here we have another, and there's not enough room in this little pocket right here to fit another hexagon to be able to have those three faces connect so that we could fold them into a shape. For these reasons, the 5 Platonic solids are the only, and Plato theorized that that made them perfect and special. Plato, among other philosophers, theorized that the Platonic solids made up the elemental sort of structure of the elements of the universe, right? We have the cube being very solid, connecting with the ground, so it represents earth, the tetrahedron being pointy and therefore destructive, so it signifies fire, the octahedron making little contact with a plane that it might sit on, so it represents air because it gives the illusion of floating. The icosahedron having a special sort of flow to it, according to Plato, and therefore representing water. And lastly, the dodecahedron, the only Platonic solid that uses the pentagon, which therefore makes it the sort of structure of the universe. Plato also argued that the dodecahedron was the sort of universal element because it was the most spherical in nature. We also had other people like astronomers such as Kepler. We've heard about him before in this class. And he sort of drew this idea of how the universe was structured based on those Platonic solids. A great many philosophers, mathematicians, and astronomers also borrowed these ideas from Plato to sort of lend their philosophies of the universe according to this sort of geometrical perfection and symmetry. And the ancient Greeks weren't the only people who thought of this stuff. We actually see Platonic solids come up in art in a lot of different groups of people. We see it in the Mayans, Egyptians, the Hopi people, Celtics, Druids, even the Knights Templar. Now, this isn't super surprising given that symmetry is something that almost all cultures across the world have sort of examined and played with. And when you think about it, if you can think about geometry in 2 dimensions being perfect and regular and symmetric, a lot of cultures extended that into 3 dimensions as well, which is why I wonder why Plato got credit for it. Was it simply because he was in a time where we were giving Greeks a lot of credit for things? Why do we not attribute this discovery to the people who clearly found it earlier? And that's a question that I still have. In any case, they're a lot of fun to draw. I'm an artist myself, and I always like to sketch these things when I teach students geometry. One thing that I've noticed is that the shift tool in Cami, which is the app that I'm using right now, really enables me to draw really lovely straight lines. And that shift tool is actually usable in a lot of different functionalities if I don't turn on sticky keys by accident by using my shift key. But one thing that my students always really love is when I draw Platonic solids for them and they sort of see how easy it is to just actually sketch things step by step. So if you're a person who's using digital learning software, I highly recommend pressing down on the shift key to start drawing any shapes that you need to draw to teach geometry, because it makes sort of the sketch of a 3-dimensional solid a lot easier, and it's really impressed my students this year. Plus they're just sort of fun. Now, notably, because we talked about these shapes in 2 dimensions as well as 3, these shapes can also be easily assembled by your students. Simply printing them out in 2 dimensions with a few key folds in place and a pair of scissors and some glue or tape, and students can make Platonic solids, which I often find that they enjoy. Anything that we do in 2 dimensions we can cut up on paper and manipulate into 3. And anytime I get to play with art, that's a lot of fun. Okay, that's all I have for you guys today.